Rana. I come from Reliance Industries, and I work as an economist in the strategy department. And as part of our things like this topic of process integration, supply chain management, and feedstock maximization is really the core part of the uh, entire oil industries, uh, how the products, the crude is converted into final products for the final use, and then how we are trying to maximize value at each step of the process. So, so upstream is one part, and downstream is the heart, and then there are the end users. And this panel is at the heart of the matter actually. So I have a very excellent papers today coming from four presenters are there. So I'll call upon one by one, and each presenter will have 15 minutes to present their paper, and then we'll see how it further goes. So without further ado, let me first invite Mr. Chiranjib. He's from Technip Energies, and he'll deliver his paper on the integration of refining with petrochemicals and specialty chemicals and fertilizers. Over to you, Mr. Chiranjib.
Thank you very much, sir. Good afternoon, everybody. Myself Chiranjib Haldar. I am acting as a delivery manager for Genesis, which is part of Technip Energies. So, as you see, my topic is integrating refining with petrochemicals, specialty chemicals, as well as fertilizer, a gateway to sustainability. So, so just a brief introduction about Genesis. Genesis is the consulting and technical advisory arm of Technip Energy. It is not at all a separate entity. It is 100% owned by Technip Energies. And Genesis, if you see, we have basically combination of consulting as well as engineering combination. So whatever suggestion we give to our client, we make sure that we can engineer it. Now going back to the presentation, so the context So the context or the motivation is basically, there is a global pressure on the refineries to decarbonize. And at the same time, with a growing introduction of renewable energy and electric vehicles, so there is a pressure that in the longer term, there will be much less production of fuel. So we need to valorize this fuel. And on the other side, there is a growing market demand for petrochemicals and fertilizer. So the topic basically to integrate fertilizer as well as petrochemical complex along with refining. So basically this integration, it will address the evolving market dynamics, and it will create a circular economical model where waste become a valuable resource, reducing both the emission as well as the raw material cost, thereby ultimately increasing the profitability. So I'll briefly cover about first is the integration of petrochemical with refining, then integration of fertilizer complex, then what are the technology available, a case study, opportunity and the challenges, and finally the conclusion. So first is like when you are integrating the petrochemical complex with the refinery. Like we know it's not moving. So there is a high growth potential of petrochemicals. Basically, if you look the refining industry, specifically in India, it is going to contribute significantly to the petrochemical industry also. Because normally, right now, whatever we are doing, we are almost in a standalone refinery, there will be 85 to 90% of production of fuel, which ultimately we are burning, that is leading to carbon emission. Whereas there is a growing demand of petrochemical. So in case we convert this hydrocarbon into petrochemical feedstock, there is a rearrangement of carbon and hydrogen, where we are not burning carbon and hydrogen. So there will be less emission, and there is a growing demand of petrochemical. India is going to contribute more than 10% to world petrochemical demand in near future. So there is a high market for this petrochemical and chemical sector. So in a conventional refinery, if we see, we are producing mostly like a fuel, LPG, gasoline, jet, kero, and that is leading to scope 3 carbon dioxide emission. Whereas when you are integrating this petrochemical complex like steam cracker and aromatic complex, we are producing good amount of other petrochemical feedstock like ethylene, propylene, butadiene, and aromatics like benzene, toluene, xylene, etc. As a result, there will be much less production of fuel, so less burning, resulting into less carbon emission, the scope 3 emission. And also, if you see the refinery of gas, basically normally we utilize it as a fuel for the refining, so thereby there is a carbon emission. Whereas it can also be utilized as a feedstock for the steam cracker complex, and in that case there will be less carbon emission from this burning of refinery of gases. Besides, this hydrotreatment section, we need HU, and there is a good amount of hydrogen required for this hydrotreatment. And from the steam cracker itself, there will be good amount of hydrogen generation. So that hydrogen also will be utilized. For this hydrotreatment section. So there is less requirement for HU section. So there will be less carbon emission. Thereby, when you are integrating this petrochemical complex along with along with the refinery complex, so we are basically addressing the dynamic market. At the same time, there will be less carbon emission. Only one thing it should be noted, that we should not restrict ourselves only to C2 or C3 like ethylene, propylene. Instead of that, we should say the complete value chain, not only like ethylene and propylene. Let us go ahead to produce HDP, LDP, LLDP, whatever are the petrochemicals. Similarly, from polypropylene we can go to from propylene we can go to polypropylene. We can find out like a 1,4-butadiene, and it can be utilized for the production of SBR, PBR, rubber industry. Similarly, there are other C4 plus chemicals also, which are also available from the steam cracker, which can be suitably recovered and used as a feedstock for the specialty chemicals. Like, there is a isobutylene, there is a dicyclopentadiene, cyclopentane, hexene, heptene, octene, etc. Those can suitably recover, and that can be utilized for production of these specialty chemicals, which is not only improving the profitability or also increasing the competitiveness. Now, next part is why I'm talking about fertilizer also, because if we look the fertilizer, the total demand was something around 60 MMTPA in 23-24. Out of that, almost 30%, 17.7 MMTPA we have to import. So there is a strong import dependency. And what are the on the right hand side, if you see the urea, almost 13% there is import dependency. NPK 10%, diammonium phosphate 60% we are importing. Muriate of potash 100% we are importing. So there is a strong demand of fertilizer driven by basically the increasing population, the food security, and also expanding crop area. So there is a huge demand of fertilizer. And if we talk about the fertilizer production, what are the key ingredients for the fertilizer? That is like ammonia, sulfuric acid, and basically the carbon dioxide. So those are the key ingredients. How we are getting ammonia? By reaction of nitrogen and hydrogen. And nitrogen we are getting from the air separation unit. Hydrogen we are getting from the SMR, and sulfuric acid we are producing in a standalone fertilizer complex utilizing the sulfur. Whereas in the refinery section, there is a impurity like nitrogen and sulfur, which is available along with the crude. So that nitrogen is converted to ammonia. So that ammonia can be recovered and used as a feedstock. Similarly, the sulfur, which is converted to H-test, what we are doing in the refinery, we are just converting into sulfur and we are sold to the market. Instead of that, we can directly convert that H2S to sulfuric acid, and that can be utilized as a feedstock for the fertilizer production. Similarly, carbon dioxide also we can recover. There is a significant carbon dioxide source available that can be utilized and used as a feedstock for the fertilizer complex. So what we are talking about, like one typical example, the sulfur basically H2S. In the Klotz process, we are converting to sulfur. So inside refinery, there is a sulfur storage, there is a sulfur dispatch facility. Then that sulfur is transported to the fertilizer complex. Inside fertilizer complex also, there will be sulfur storage. Then we are melting the sulfur, there is a burning. Then ultimately conversion of sulfur dioxide to sulfur trioxide, followed by sulfuric acid generation. Whereas if we are directly converting H2S to sulfuric acid, that means all these intermediate steps related to the storage, the transportation, the melting, burning, etc., that can be eliminated. So there will be significant capex saving, significant OPEX saving. There will be much less plot area requirement, much less manpower requirement, and much higher efficiency, leading to reduction of carbon emission. So this is one typical example for H2S. So this integration concept basically including refinery, steam cracker, aromatic complex, it is not only addressing the growing demand, the changing market dynamics, but there is some this ammonia, H2S, and carbon dioxide. These are the low value product. It can be valorized to produce this fertilizer complex. Thereby, it will lead to improved economics. Then there will be improved operational efficiency, followed by less environmental emission, and ultimately, with production of this fertilizer complex, will be contributing to self-reliant India. Now, question is like on schematic diagram, if I can show, like On the right hand side, if you see, this is the fertilizer complex, and the left hand side, we have the refinery and petrochemical complex. So fertilizer complex, standalone fertilizer complex, we are generating sulfuric acid from sulfur. Whereas as we discussed, in case we are directly converting H2S to sulfuric acid, that means this sulfuric acid, standalone sulfuric acid unit is not required inside the fertilizer complex. It can be totally eliminated. There will be capex saving. Similarly, we can recover carbon dioxide and ammonia and use as a feedstock for the fertilizer complex. Now the question could be ammonia. How much ammonia are you going to recover? Is it good enough or sufficient to cater the demand of fertilizer? Question is no. But if we look at the refinery and petrochemical complex, we are generating good amount of hydrogen from the steam cracker. Besides, nowadays we are going for green hydrogen generation. So what is happening in the HGU section, which was initially designed for the standalone refinery, there is a surplus capacity available. So that means we can produce surplus hydrogen, and this hydrogen can be used as a feed source for the fertilizer complex. Similarly, in order to produce ammonia, we need nitrogen. Nitrogen can be generated from the air separation unit. Inside refinery also we have air separation unit, and this air separation unit normally it is designed. The governing case is for the a startup or shutdown, purging requirement, or like catalyst regeneration. So which is not like a normal operation. So during normal operation, there is a sufficient potential or surplus capacity available. This nitrogen can be routed to the fertilizer complex, where it can be suitably utilized to produce ammonia. So thereby, when we are combining this fertilizer complex along with the petrochemical complex, so thereby the capacity of the SMR, the capacity of the air separation unit, all will be reduced. So there will be capex savings significant. So all this along with sharing of their infrastructure facility and common utilities, leading to the much lower capex if we compare with the standalone fertilizer facility. Now, question is, do we have the technology available for this integration? For petrochemical, I think it is well known. There are several licenses available and commercial available, technology available, no issue at all. For specialty chemicals, there could be some sort of issue because normally it is closely guarded technology. So here, maybe we can do some sort of joint venture with the technology supplier or with the producer in order to go for this specialty chemicals production. And related to this ammonia recovery, we all know there is sour water stripper available in the refinery unit. So in a two-stage sour water stripper, we can recover ammonia from the top of the second column. So that ammonia can be suitably treated to produce a desired specification of ammonia, which is required for the fertilizer complex. Similarly, for the acid gas conversion to sulfuric acid, there are licensors available. There are a lot of licensors available, and it can be easily converted to sulfuric acid. So there is a proven technology available. For carbon capture also, there are multiple options available, whether we are using amine solution or we are using like membrane separation or cryogenic process. We can utilize this technology, we can recover carbon dioxide, and we can utilize for the fertilizer complex. So on typical case study like 9 MMTPA refinery and petrochemical complex, if we consider standalone refinery, there are only like the fuel. But when you are integrating with the petrochemical complex, like case 1, there is a significant amount of feedstock like LDPE, HDPE, polypropylene, acetone, phenol, etc. produced. So thereby, if you see, there will be gross revenue margin that is jump from 100% to 206%, so more than 100% jump. And at the same time, if you see the emission reduction, there is a 26% reduction. And case 2, when you are recovering this ammonia and sulfuric acid, so there will be further improvement in the GRM as well as further reduction of emission. So even if I talk about only related to the fertilizer complex, so like if I consider feed nitrogen content of 0.1 to 8%, that means 9 MMT refinery would have a potential of about 40 tons per day ammonia generation. So that means almost like $6.6 million of USD, what we are right now burning, basically this much of ammonia, we are burning every year inside a 9 MMT refinery, whereas in 2024, India imported $1 billion of ammonia. And if I consider total refining capacity of about 258 MMTPA, then there is a potential of 0.37 MMTPA ammonia recovery, which can be utilized to generate DAP of 1.4 MMTPA. So that means my DAP import can be reduced by 29%. So it is contributing to the self-reliant India. Now, opportunity, definitely along with the opportunity, there will be a lot of challenges also. One is related to availability of technology, as we discussed. Yes, this basically the technology for specialty chemical, those are closely guarded. So the solution could be like forming a joint venture. Another option is limited availability of C4 plus olefins, but fortunately the demand for this specialty chemicals is also moderate. So this amount, whatever available, that will be good enough. And for ammonia, we have already discussed, yes, additional ammonia can be utilized by utilizing this hydrogen and nitrogen, surplus hydrogen, nitrogen, whatever available. Another is like, okay, solid handling, but solid handling is not like a new it can be easily done based on the leveraging on existing operational expertise. Another critical point could be the permitting and regulatory hurdles, because one side it is like a Ministry of PNG, another side is a Ministry of fertilizer. So this can be, we can have a joint policy framework to address the concern, leading to the easy approval or smooth approval and coordination process. So moral of the story, okay, there is a global pressure on the refinery to decarbonize it, and at the same time, with introduction of EV, sustainable energy, etc., so there is a pressure to move from fuel-based to other base. So here, when you are integrating the petrochemical complex along with the refinery, so this is there is a rearrangement of carbon and hydrogen. So we are addressing this requirement, and at the same time, the remaining low-value streams like ammonia, carbon dioxide, H2S, etc., those can be valorized as a feedstock to the fertilizer complex. So this integration, basically, it is addressing the evolving market dynamics and create a circular economical model where waste become valuable resources, reducing both the emission and raw material cost, and thereby ultimately driving the improved profitability. If I talk about the key enabler or success, yes, technologies are already available, there is a good market demand, there is greater economical resilience when you are integrating it, and it will lead to reduced carbon footprint. And ultimately, we are contributing to self-reliant India. So why to wait for? Let us break boundaries together to engineer a sustainable future. Thank you very much, everybody.
Thank you very much, Mr. Chiranjib. I think it was a very exciting presentation. You captured 2 case studies, and yes, it highlights that while you can strive to integrate and increase the revenue, at the same time you can reduce the emissions. So point well taken. So yeah, next I'll call upon Mr. Abhijit Pal. He's from Honeywell UOP, and his paper is on improving ethylene profitability, paradigm changing UOP NEP process. So let's learn about the new process that UOP has. Thank you.
Thank you, Dr. Rana, and thanks to IEW. It's an excellent audience, and it's a great honor to present today a paradigm-changing UOP NEP process. It's a new one. It basically will redefine the way we deal with the petrochemicals, and that is what I will talk in my presentation. The presentation is basic. So first, forward-looking statement, whatever is, it says a policy that, whatever we are presenting here is with certain assumptions in our best of knowledge, but that does not give it as a guarantee or something. So first I will give some context, and after giving the context, we'll talk about the technology, and then we'll conclude with 2 case studies. So first we'll try to build the context on what about the petrochemicals. Now petrochemicals essentially is driven by the 2 major things, which is ethylene and propylene. The market says that the global ethylene and global propylene, both these is expected to grow about 3% in an annual basis. Now there is another interesting finding which has come to the Wood Mackenzie study, that there is also another force which is increasing the demand. What it is? That some of the existing petrochemical complexes, some of those are a bit older, like ExxonMobil's Singapore plant. There are cases where in South Korea they are closing down the petrochemical complexes, and why they are doing that? They want to take on the new technology which will have a bigger scale, because in last decade or so, China has improved significantly in this petrochemicals area, and they have used this scale and new technologies to get the market. So if this happens, the study says, then the demand will go up probably by 6%. So there is always a chance of increasing demand for ethylene and propylene, which is the key of the petrochemicals. Now, what is the challenge in this light olefins industry? We are talking about mainly ethylene and propylene, not the isobutylene or butylene one. Now, this ethylene and propylene basically mostly is made based on the steam cracker. And in the steam cracker, we can have a liquid cracker, we can have gas cracker. Now, liquid cracker has a less ROI, it has a high capex, and it also have a concern on it's a energy guzzler. So with all this focus on sustainability, there is a pressure on how we can go up on the liquid cracker. When you talk about the gas cracker, like ethane cracker, another problem is its supply. It's highly dependent on Middle East and US. Saudi has recently increased their ethane prices, and United States it's expected to increase the prices. Like recently, we have seen people are looking for ethane. I mean, ONGC recently had this vessels they have bought for the importing ethane from US. Now that is expected to go up, and plus there are lot of issues on the various political issues, which might create the dependencies too much. On the also, the fact that the cost of this ethylene cost is highly dependent on this naphtha cracker. So if we find a better way to produce this ethylene and propylene than the typical naphtha cracker, that probably is that paradigm change, and that is what is requested. So when we dig with that, let's go back to a bit on a molecular level. And if you see from the slide, if you see the yield of the ethylene comes best if it's cracked from ethane. Because when you crack from ethane, your all these pi oils and pi gases are released, aromatics are less, and you get a maximum amount of ethylene. The same goes for propylene. If you get propylene from PDH, propane dehydrogenation, then you have the maximum propylene production. So the bottom line here is, if we can get directly from the ethane and propane, both ethylene and propylene, that is where we can get the best yield. NEP addresses this. The new technology I'm talking about addresses this. And here I'm just giving a small details on this. So NEP is basically a free preparation unit for the steam cracker. It takes the light naphtha, it cracks it to ethane and propane. If you want, you can have propane. If you want, you can have only ethane. Then obviously there is a separation section. The ethane can go directly to the ethane cracker, and the propane can go to the propane dehydrogenation. And this gives a significant increase of light olefin yields, somewhere between 50 to 70%. And because the yield is higher, light olefin yield is higher, byproducts is lower. If you have a same capacity of ethylene cracker, then actually you need a less crude or less feed. So both these basically drives to the reduction in carbon number and obviously the lower capex and opex. One of the key aspects of this NEP is its flexibility. You can have a ethane to propane ratio pretty much from infinity. Means you can have only ethane, or you can have a certain ratio of ethane and propane. And because of this tunability, it can be applied in either whether it is a grassroots plant, or it is a brownfield application or greenfield application. You can put it as a part of your existing cracker. You can use it when you consider, as Chiranjib was saying, that that when you move from crude to chemicals and you integrate refinery and petrochemicals, this is where it can fit in. So because of this flexibility, NEP has become a good and a paradigm change. And I will give that with two examples, two case studies. The first case study is a brownfield application. This brownfield application is for the existing mixed mixed feed steam cracker, and here the customer has to revamp this steam cracker to reduce the propellants, reduce the byproducts, and increase the ethylene production. On the left hand side, you can see basically is the current configuration is a very typical mixed feed steam cracker with two liquid furnaces, two gas furnaces. The gas furnaces basically is give mostly on the propane. The naphtha is fed to the liquid furnace, and there are two flex furnaces. The proposal here is to take some of the naphtha, put it to a NEP unit, convert it to ethane, and that ethane then fed to the flex furnaces. And here the advantage is you need not have to change anything in the propane furnaces, neither you have to change anything in the liquid furnaces, only in the flex furnaces you put the NEP and put the ethane. And the result, if you can see, what essentially this plan shows that when you put this extra naphtha and some additional naphtha to this NEP, get this ethane and put it to MFC, you increase your ethylene production by around 300 kMTA. And that comes from reduction in propylene. That's what the customer wanted. So they reduce the propylene. And one of the most important is they reduce the production of pi gas and pi oil. And this gives with incremental this IRR is about 20%, and which is a significant, because you need not have to change a lot of stuff. You have to put a NEP unit and you are getting a desired ethane product. The second case study is on the greenfield application. Now this greenfield application is something which is a very typical one. You have a crude, you have a cracker complex. Here the crude is a bit lighter one, which is more condensate type of crude, API 47. The customer here maximizes the polyolefins, but they have not fixed the ratio of polyethylene and polypropylene. And it's important because that is what we will show in the slide. And obviously they want to reduce the byproducts, like especially like the pi gas and pi oils. And they have around 100 kbsds crude. On the left hand side, again a conventional crude to chemicals. You have a CDU, you have a hydrocracker complex, and you have a mixed feed steam cracker. On the right hand side, what we have shown is instead of having a hydrocracker, you use the advanced hydrocracker. The key aspect of this advanced hydrocracker is it converts mostly to your light naphtha. And once you get that light naphtha, you straight run naphtha as well as this cracked naphtha, you put it to NEP. And from NEP, here you can change, like I said, the tuning is a big thing. You can change whatever you want, how much propane you want and how much ethane you want. The propane goes to the PDH instead of mixed feed cracker, and the ethane goes to the ethane cracker. And what is the result we get? So on the left hand side, if you see in this conventional crude to chemicals, you have total about 53% of polyolefins. But when you come to the NEP based crude to chemicals, it can go to 69 to 78. There is a variation. The reason of this variation is customer has not fixed the ratio of polyolefins, polyethylene and polypropylene. So we did some tweaking. We worked in a 3 different configuration, and it basically changes the ratio of ethane to propane. Where in the crude to chemicals you get a fixed ethane to propane. Here you can vary this ethane to propane based on whatever is the demand. And it gives an incremental cost of 10 to 20% of the capex. So if your capex would have been 100 billion, then it is about between 110 to 120. That's the extra investment. But with this extra investment, you get an incremental IRR about 4 to 5%, which is a significant. and obviously your NPV has gone up. So with this tweaking, that is what you can do within your existing system. So this is the second case study. Now this technology is now ready, and we just concluded a Schedule A or basic design package for a demo unit in China. Hopefully next year if I come here, hopefully we can present you on what is our finding from the demo unit. In addition to that, we have already signed the MOU with Petroleum in Saudi, and we are at the advanced stage of signing off. Probably this week we will get it signed off. We are also working on a huge complex, and that will be a grassroots petrochemical complex, about 3,000 kMTA. And that is where, again, we are in an advanced way of signing off the Schedule A. So there is a big market demand. We see a lot of interest here. We also have a modular options of making it small but fix it in the, especially in the brownfield, and we are ready to license and further guarantee this. So that's all about this. And NEP, we have a belief that it has a tremendous potential. We are talking about the next generation as well, where we will make a significant changes, but it probably is 4 to 5 years down the line. But at the same point of time, we see a lot of demand here. And if in case you are interested, Honeywell has a stall here, and I'll be available in that stall, or our colleagues will be there. We'll be happy to talk more about the NEP. Thank you so much. Thanks, everyone.
Thank you, Mr. Pal. Thank you very much. And without further delay, let me call upon Mr. Shekhar, and let's learn about what BPCL is doing with advanced optimization for the refinery planning.
Good afternoon, everyone. Hope I'm audible. Thank you, sir, for the introduction. So today I am going to share BPCL's journey of usage of Avira Spiral software from basic assay cutting tool to advanced optimization. Yeah, this is about BPCL. So hope everyone knows about BPCL. We are the second largest oil marketing company in India, third largest refining capacity, and fifth largest by turnover. So here we start the actual challenges which a LP modeler faces. So our refinery operations are very complex in nature. So to model those complex operations in linear mathematical equations becomes very difficult. And over and above that, there are special operating conditions, and their real world scenarios are there, their delta vectors are there, so they are very difficult to model it. So what happens because of this, our plan versus actual deviation occurs. So whenever there is a plan versus actual deviation, there is a margin leakage is there. So what we are planning, we are not getting that. So based on that, I am not doing the evacuation or distribution plan also. So this is the place where I am losing the actual margin. So here we have taken 5 scenarios, and we try to model with the help of our Avira Spiral software. So already we have the existing software, so we have done few changes in that, and we have modeled 5 scenarios. So these are the 5 scenarios. Slow processing is one of the things that every refinery faces. During upsets, they have to route their slopes to off-spec tanks, and later they reprocesses that. So generally we don't have a crude assay of a slope tank. So there in subsequent slides we'll say how with the help of Spiral we have developed the assay of slope tanks. Another thing is intermediate evaluation. So normally in market sometimes high sulfur diesel, high sulfur VGO and vacuum residue is available. So due to infrastructure limitations, we cannot directly take those intermediates in intermediate tanks and process in the secondary units. So what happens, we have to take those in crude tanks and then process first in crude tanks, then subsequent to secondary units. So there also we don't have assays of those intermediates. Again, my break-even point calculation becomes difficult there. Third one is special operating conditions. So maybe other refineries will not be facing it, but one of our refinery faces that every year 4 to 5 days will take a shutdown of our vacuum column, and that our crude column will be running at reduced throughput, and whatever RCO is there will be routing to our crude tanks, and they'll reprocess in subsequent months. So there it becomes very difficult to predict the bottom products generation. Fourth one is crude evaluation. So more than 5,000 crudes are available. So normally we evaluate 500 to 600 crudes every week. That is what BPCL does. So sometimes we misses some crude. So with the help of spiral, with a single click, we'll see which crude can show the value in our system. Later we can do the detailed evaluation of that crude. So this will give the direction that we can process that crude or not. Fourth one is cut points. Normally cut points in our refinery crude assays are static cut points. So we cannot target a particular property. So here we use the spirals feature of dynamic or target cut point. So here we have used the dynamic cut points, that also we'll see in subsequent slides. So first thing is slope tank modeling. So slope tank modeling, what we have done, we have just tested the 3 to 4 properties of our slope tanks. One is sulfur content, density and viscosity. Moreover, MCRT also we can test. With the help of that 4 properties, we can generate a assay with the help of assay synthesis feature of spiral, and that can be used as a pseudo crude, and that we can integrate with our LP tool, and we'll know that will behave as a crude, and we'll know what are the product it is going to generate. Over and above that, we'll know if how much slope we can process. If my slope contains very high quantity of vacuum residue or very high quantity of naphtha. So any physical limitation in my crude column, that also able to know with this slope modeling evolution. Second one is intermediate product assay generation. Suppose we are taking intermediates in our crude tanks and then processing in crude units. So it becomes very difficult to calculate the break-even cost. Over and above that, suppose we are just neglecting the operations of crude unit. So 2 things will be missing. One thing is like any limitation will be facing those intermediates in our crude unit. Moreover, the utility consumption of the crude units. So here also we have done the same thing. We have used the product synthesis feature of spiral, and with 5 to 6 properties we have generated a pseudo assay of that particular product and used that as a assay in the crude unit. So third one is vacuum column shutdown modeling. So that one of the refineries, our Mumbai refinery, faces this issue. So there what we have done, we have taken a particular crude and cut that crude in 2 parts. One is till diesel cut, another from VGO cut to the VR cut, and we have treated those two as a separate crudes, and these have helped us in predicting my exact FO generation. So single crude cut in 2 pseudo crudes, and we are able to predict our products. Fourth one is dynamic optimization in that freeze point. So one of the refinery what we are facing is freeze point, our ATF freeze point. So what we are doing at that time, whenever any particular crude is coming and freeze point is not meeting, we are dropping certain quantity of heavy caro into diesel. So in that particular refinery, we are having limitation in diesel treating unit. So we are not able to evaluate the accurate crude every time. So we will buy some crude. When we will process in actual scenario, we are forced to do the crude cut because we have a high inventory of diesel. So here what we have done, we use the target property function of spiral. In that, instead of having a static cut point of caro, we have targeted the freeze point. So every time any particular crude is coming, the freeze point will, the cut point will change based on a static freeze point. So static cut point has been changed to static freeze point. This has helped us for better crude evaluation and better utilization of our downstream units. Fifth one is straight run product value. So there is a feature in spiral in that straight run product value. So we can just assign values to what are the products we are going to make from a particular crude. So this will vary from one refinery configuration to another refinery configuration. So with that, we'll get an idea like how a crude will give value to a particular refinery. So this will not help us to accurately calculate the value of a particular crude, but this will give direction. So if we know more than 5,000 plus crudes are available in our SA system, and we are evaluating 400 to 500. So if the help of this thing, we'll know, okay, we are not missing any crude. If a new crude is coming, I'll just put that crude and see if it is giving value to my system. I'll start evaluating the similar same in my system also. These are the real world scenarios. So first one is vacuum residue processing. So one of the unit upset, we are forced to route our vacuum residue to one of the slope tanks, and later we have reprocessed the same. So with the help of our assay synthesis, we generated the assay of that particular crude tank, and we are able to predict the actual numbers of my FO production, and we avoided the distress FO exports. Second one is our vacuum column shutdown. So there also, because of additional RCF generation we have processed in the subsequent months, there also we are able to predict our FO generation. And Mumbai refinery is such a location, we are always concerned about the tanks. So predicting the correct amount of product becomes very important there to avoid the distressed sales and distressed exports. Fifth one is HSD, that is high sulfur diesel or intermediate import analysis. So similarly, we have just created a pseudo assay of that particular diesel and processed in our crude unit, and there we are able to get the accurate break-even cost of that particular intermediate. So with this is a strategic benefits and future impact is there. So there is high possibility we can use in digital twin also. So similar, like which are the crude tanks we are charging, the 4 properties we can test, and with that we can generate the assays, and we can see what are the products we are going to get out of it. And with that we can standardize our processes also, and constant our yields we can get it. Another are economic advantages is our better break-even analysis, because we will be knowing what ISD I am buying and how much value it is going to give when I am processing through whole refinery operations. And with 5,000 crudes, with a single click we will know which crude is giving value to me and which crudes I have to put more focus. We can get more optimized crude mix there. Then this is the way forward. So with the help of this, we will be evaluating more crudes. We will try to model or replicate more refinery complex operations into LP model, and last we want to reach towards our digital twin. Thank you.
So thank you, Mr. Shekhar. Let's get on with the presentation because we are just about on the schedule. So Mr. Pramod, the last presentation of the day of the session is from HPCL, and we will learn about another technology, the HP NTO technology.
Good afternoon, and thank you, Chairperson. So I thank IEW committee for giving us the opportunity to present the work what we do at HPCL R&D Center, Bangalore. So before we get into the presentation, I just wanted to set the context for this innovation what we brought. Typically, we have seen in the earlier presentations, and also we know worldwide, if you want to make ethylene propylene, the only solution is the steam cracker. And we know this is a thermal cracking process, right? So we know from the chemistry and the chemical engineering point of view, if we use a catalyst, probably we can reduce the temperature and we can improve the selectivity. That is well known. So that's the problem definition we took at HPCL R&D Center, and we came up with the innovation, and we call this technology as a NOVA HP. NOVA stands for Naphtha to Olefin Value Addition Technology by HPCL, which we believe it's a viable alternate technology for the well-established, well-proven naphtha cracker technologies. So that's the context. I'll get into the full presentation. So the content of my presentation is definitely the comparison with the thermal cracking process, what is the novelty of this HP NOVA process, and where we have taken this innovation. In our HPCL R&D, whatever we do for the markets. So we have taken this innovation out of our lab, and we'll discuss where we have taken this innovation in the market. and followed by the summary and the way forward. Right? So typically if we see in the refinery, if you want to produce the light olefins, what are the streams and the intermediates available? If we start from the ethane, so we have the ethane, propane, butane, gas oil, naphtha and the heavy oil. And what are the solutions or the technological options available? So if we get into the lighter molecules like ethane, propane and butane, so probably the steam cracker is right now the solution. But if we get into the heavier molecules like gas oil or partly naphtha in the heavy oil, we can think about the high severity FCC. That's the current technologies available to us. So this is just a glimpse about the same thing. I'm not getting into what are the value additions from the each like olefins, but directionally if you see the left side, the ethylene is mostly coming from the naphtha and the ethane using the steam crackers. Small quantity, 5 to 6% will come from the FCC route. If we go to the propylene, yes, FCC, high severity FCC produces propylene, but still it is lower than the naphtha cracker. But if you want to produce butenes and all, their naphtha crackers or the, FCC, high severity FCC comes into the picture. So that's the kind of the shift if you want to produce whatever olefins we want. The below slide shows about the end use of the ethylene, propylene and the butenes, which I am not covering now. So let us pause a little bit and see what is the current scenario of the India, what is the demand figure and what is that capacity available in the country right now to produce ethylene, propylene. So currently itself there is a significant gap in the ethylene and the propylene. But if we talk about 2047, when we are thinking about India has to be Viksit Bharat, so definitely there is a significant gap in terms of the ethylene and propylene. And to just give a numbers, probably every 2 years we have to put a good size crackers. So do we need to put a steam crackers or there are other solutions available to us, India-centric solution. So probably we look into those numbers as well. And just to give a numbers like CAGR growth of the ethylene and the propylene is hovering around 3 to 5%. So right now we are looking into the thermal and the catalytic routes. So if we get into the catalytic routes, probably the well-established routes are either we have to go to the fixed bed process or the fluidized bed process. So from the innovation point of view or the technology development point of view, we are trying to address at the initial stage of the technology. Because if we don't choose the right path, probably it will take a long time and we have to again go back in the development phase. So for this naphtha cracking technology, we have selected a fluidized bed technologies. We'll discuss why that fluidized bed we have selected, not the fixed bed. So it's a little bit reaction mechanism, but I think post lunch I'll try to make it little easier one. Because if you see the thermal cracking mechanism goes with the radical formation, as free radical formation. And free radical formation is the limiting step. I mean, what it means is you have to increase the temperature to a very, very high level, around 800 and all, so that the radical formation starts. Once the radical formation starts, it goes into the beta session. And if we see the kinetics of beta session and the hydrogen abstraction, beta session predominates and the stable molecule is ethylene. And that's the reason in the thermal cracking, we produce more of the ethylene. And we know when the termination happens, the radicals recombine and we'll end up in the products. And if that combines in a bigger ones, so we'll end up in a heavier molecules, which we call pyrolysis, fuel oil, or it can be a butadiene. So that's the kind of the mechanism we follow in the thermal cracking. But let us look into the catalytic route. So catalytic route, it starts with the protonation because we are using the zeolites. So when it starts with the protonation, the mechanism follows is the carbocation. And we know the carbocation tertiary will be more stable than the secondary, than the primary. And that's the reason in the FCC, if you see, we get more of the aromatics or some isomer or the branch molecules. So that's the mechanism the catalytic cracking follows. Now the right side picture shows what is the kind of the activation energy can be reduced by use of the catalyst. And that's the key thing we are trying to use in our innovation of the HP Nova. And the biomolecular mechanism also happens of the carbocations, and that leads to the coke and certain heavier molecules. So I think most of us know what is the difference between the fixed bed and the fluidized bed in terms of this naphtha cracking solutions, what we are looking. The biggest advantage in the fluidized bed is we are able to contact per molecule of the feed to the catalyst is much higher. So we are using the catalyst activity as well as the heat what the catalyst carries, and that's the reason we are able to maintain the activity for a longer time. And that was the choice for using the fluidized bed for developing these technologies. So I'm not getting too much into the details about what are the factors which improves the olefins. Directionally, it follows the FCC route, like you have to be cat oil higher, temperature has to be higher, pressure has to be the lower, steam to hydrocarbon ratio has to be optimum, and yes, catalyst has to be unique catalyst. Otherwise, it will land up producing aromatics if we go to the conventional Jetsam 5 catalyst. And that's what the uniqueness we have brought in from the catalyst side as well. So what are the key features of the HP Nova process? It is built on a well-established fluidized bed reactor. We know how FCC operates. So this is built on the FCC platforms. And see, if we see the steam cracker, there is a limitation. The naphtha has to be pre-treated, sulfur has to be reduced, there is an olefin requirement, there should not be any olefins, there has to be a different cut of the feed. But if we take this platform, we can process 100% of the naphtha. There is no pre-treatment required for these technologies. And in this technology of this HP Nova, there is no butadiene production unlike the steam crackers. Other advantage is like if you see the steam cracker, P by E ratio is almost fixed, 0.5. But here you can go as 2 P by E ratio. That's the kind of the uniqueness. And we are also able to manage the heat balance. That's the key challenges we are seeing when we are trying to process naphtha into the FCC routes. The other advantage, if you see, right now worldwide, probably as far as we know, there is no technology to crack the diesel and the kerosene, and that is going to be surplus in many of the refineries. So if we take this platform, we have seen we can crack kerosene and the diesel to the significant level to the olefins and the aromatic. So that's the kind of the flexibility this technology brings in, besides having no pre-treatment requirement of the naphtha. Yeah. So this is the typical refinery configurations, not having any petrochemicals. So if you want to put naphtha into these HP Novas, so instead of the steam crackers, we can consider putting full range naphtha, and whatever the olefinic naphtha comes from the FCC or even the delayed coker, that's the excellent feed for this unit, HP Nova. So we can maximize the olefins and the aromatics from this technology. So now let us think about a technology. What are the key things it has? It has to have a process, it has to have a catalyst and the differentiators. In terms of the process, it is well established fluidized bed, so there is no challenges in the scale up. It is a circulating heat balance unit. We are addressing the co-killed with our unique catalyst solutions. In terms of the catalyst, yes, it's a very unique catalyst, not the conventional Jetsam 5. And this catalyst, we have scaled up to 15 metric ton. So there is no ambiguity on the catalyst operation as well. In terms of the other differentiators, high P by E ratio. In terms of the steam crackers, if you compare energy requirement and the CO2 reduction, it's much low per tons of the olefin production. So now let us see how we started our journey. If you see, we started this project in 2020 with a concept to address the challenges or the gaps existing in the naphtha cracker technologies. So with the 20, we've taken the project, we more or less formed the catalyst formulation, bench scale we have done up to 22. We put up a pilot plant and 1 kg per hour heat balance pilot plant, isothermal pilot plant is running in our campus. We have completed the pilot study. Yes, there comes the key thing. Now at the R&D side, we have done the technology. Now the key things for any R&D, probably my colleagues will agree, we will go to the management and ask for demo plant. Now you know the demo plant for us will cost more than 100 crores if we want to put up a 80 KTA plants and all. And besides that, there is a lot of engineering challenges. So what our management said, we don't think about putting up a demo unit, instead go to the best person who should vouch for your technology. And that should be a credit to you. If they vouch, probably your technology is okay, and they should take it forward from the pilot scale. Why you want to waste another 3 years to put up a demo plant? And that's where we went and we discussed with Lamas, and after complete due diligence, you know, that's a really actually complete due diligence. And we are proud to say that Lamas, who is one of the world's best steam cracker technology licensor, has adopted this technology, and they will be offering this worldwide for this technology. Yeah. So in terms of the yields, I am not getting, it is more than the 55%, and to be specific, we are close to 70%. We are not giving the numbers and all. Butadiene is too low. Steam to hydrocarbon, if you see the cracker, it's 50%. In this, to be very specific, it's around less than 20%. So the economics, we have seen, it's a higher revenue generation, OPEX reduction up to 30%, it's a lower CAPEX, no feed purification, butadiene is very low, because we are seeing if you put a steam cracker, butadiene handling itself and the marketing of that is again a challenge. P/E ratio is highly flexible, we can vary that. In terms of the environment, yes, it's low energy, so we are saving the CO2 per ton of the olefin production. That's the advantage, less steam consumption, and we believe this can be a sustainable technologies if you want to adopt or put this technology for the future olefin production. With that, thank you for the patience here.
Thank you, Mr. Pramod. So with that, let me conclude, and thank you once again to each of the presenters, and thank you each of the audience members for your patient listening. Thank you very much.